Well, good afternoon. You'll see two names on this presentation. Unfortunately, Mr. Harley was not able to make it, so I'm on my own. So we're going to learn some terms that might be different than what you think. So first off, high level is the 30,000-foot view type of a model. So I'm going to talk about what the Warner Robins Air Logistics Center does, what Art of the Possible is, how we model each gate, utilization concerns, and how I use the hold, delay, queue, block logic, and then the restrict area start, and then how fast the template is to use, because in the previous slide I made a big claim about increasing the speed of model development. And then we'll look at the KPI dashboard. That's the standard one that we use. So in Warner Robins, Georgia, we are one of 3 bases, and we take the largest aircraft that the Air Force has, the C-5, the C-17. There's so many C-130s that multiple bases actually repair the C-130, and we repair the largest fighter being the F-15. I put the dimensions on there so you can see the scope of our problem. We do the repair and overhaul, so the largest maintenance that's required on the airplane. So the plane lands, they take the control surfaces off, other parts off the aircraft, and they send it to another group, which I talked about yesterday. And things get depainted, they get fixed, replaced, then it all gets put back together, and we test it, and then hopefully it can fly away. Okay? So the art of the possible is our management system, and it's in a book. It's not a computer management system. It's how we want our leadership to behave and operate the base. So that's outlined in the manual that you see up there, AFSC H60-101. That's publicly available. The reason we do this is you see the little org chart there. We have the sustainment center, and underneath that is the 3 bases. So we're doing all different aircraft overhauls, so there's hundreds of different processes that we have to follow, and we have to report progress up the chain of command. So if everybody's doing their own thing, it doesn't work out for the chain of command, because they have to learn everybody's system of reporting up, and what does that mean? What are you doing there? So we have in the art of the possible, we have what's called a gated process or a process machine. Machine is not equipment. Machine is just something that does work. And it has gates in it. So you can see here, it's an example, came straight out of the book, of a 5-gate process. And what we do is we figure out how much WIP, how many items can we work on at the same time, and how many flow days it should take. Okay? We're in a unique situation because sometimes our things take a month, 2 months, 3 months, maybe longer. So our unit of measure is days, flow days. So in order to take that gated process and put it into a simulation really quick and just make sure that the calculations were right, I came up with this model. There's 12 steps in there, alternating color, the green and the gray bar. And the solution is a standard template designed in AnyLogic, and the template enables the engineers to easily modify their gated machines rather than create a model from scratch. This is a zoomed in area of the thing. So what we want to know is the effects of variation and dependency. So we would take this basic model and add in resources, other logic flow things that might be different, and that ends up changing the calculations that I showed in the beginning. So what is the in-work utilization? How are my queues filling up? The actual time that it stays in the system, and then the actual throughput at each gate. How are they really performing? Okay. Now, if you look on the left side, you'll see some radio buttons. What those are is, instead of the person putting in what the distribution is, they can click those radio buttons. So if they want to do some extra validation or verification, you just click the standard single time. So let's say you want 3 days instead of running a 1 to 4 day triangular distribution. So it allows you to change the distributions right there in the model. You can even do it during model run. So this is one of the problems we had. The delay block has a utilization data set built into it. But if you set a time up in the delay block and that time is done and it can't leave, it stays in there and continues to say, yes, you're fully utilized within the delay block. Okay? There's good reasons they did that. It's not a bug or anything. So what I have here is a simple model that a beginner modeler might make the mistake on. Is I got a delay process, I got a process, I got a process, I got a process. The chart that says not real, you can see the first step has 100% utilization, and then it kind of steps on down. Well, I've modeled it off the screen here with putting a queue after each delay, and so you can see what the real utilization is. So it's off. You can see the top difference there is 13.1% difference in delay. So that was something we had to deal with. So simply in the model, you put a queue after it so that when the time in the delay is done, it can get out of there. It has a place to go. So that allows the delay.stats utilization thing to work in the bar chart for utilization. So I already talked a little bit about how the delay block is utilization, but it's the current size divided by capacity and then averaged out. And then the queue block accepts the next agents. And if the next delay block is allowed to accept the next item, it lets it on through. So I was like, okay, well, how do I take 2 blocks and make it so both blocks can only have 4 items in it? So being a computer programmer, I went there first. So this is what I came up with. Put a hold block in front. When anything enters that hold block, you turn that hold block off so it can't accept any. When anything leaves the queue, it's now down 1 item, so you can add another one in, so it unblocks the hold. And then this was the tricky part. In the delay block, at the on enter, you have to say, okay, I opened up my hold gate, it entered the delay block, I need to count, because if I don't have 4 in there yet, I need to reopen that hold and let another one in. And then at the delay block on the at exit, not on exit, very important, you just use the same code. Okay? So that ended up working really well. Some of you modelers might be cringing inside right now, going, there's another way. Well, in computers, there's always at least 3 ways to do things. So here's the simple way. Okay, no Java programming at all. you use restrict area start and restrict area end. This does have some advantages, as you could hold 4 in the delay block, but say I can have a total of 6. So I'm allowed to have 2 in the queue and 2 in the delay block, which in our case is where the work happens in real life. Now let's get into the KPI chart. Okay, this looks very busy, and yes it is, but because we do art of the possible, we all speak the same language. We understand what these things mean. So the first area is my time and system histogram. How long in the time start end that I'm concerned about, what does my time distribution look like? And that'll usually surprise people. Right here is my in-work utilization chart for the 12. Remember, I had 12 things set up. That's why you see 12 bars and 12 sections. This is just a test. It's good when you create a template that the sample data that you put in there gives you some somewhat exciting results, if not really exciting results. So there's kind of up and downs in utilization here. And now this is very important. This would be the third gate, because it's the third section that I've got sectioned off. And I have a grayish silver bar that I think it says 2. So there's 2 items being worked on, and there's one red. That red one is the one that went into the queue. So the gray bar is the delay. The red one is the one in the queue. That means I could be working on another one, but I can't, because that black bar is the next queue in between, and the system's full. I can't make anything move farther down into the other gates. So this kind of charting is very easy. You just look for red and black bars as the whip is moving through. Problem developing. Let's find out why. And then down here, in theory, or in Art of the Possible, it's a theory of constraints-based management system. So we have throughput and takt time numbers here. Throughput and takt time are just inverses of each other, either units per time or time per 1 unit. It depends how fast you're going is what makes sense to the human. So if I say, oh, you're going 0.15 days per item, well, do you know how many to make a day without getting the calculator out? So that's why we show both. We can also set how many days we want to look at. So how much would we get in a month? That's a little yellow box to the left there. How many days do we want to get in a year or a month? We can just change that number and it'll redo the calculations for you. And that's running as each item goes to a sink, it recalculates that table. Otherwise, it's switching too fast and you can't keep up with it. Okay, so I talked about speed. So let's get into the process for designing a model. So we'll have 6 steps. So our first step, we need to model the work. So you design the logic, you create visual output to understand what the model's doing. You have to validate and verify is the model correct that you created. Well, we're not doing that from scratch. We're using the template. So arguably, we're saving weeks. I think a model like this wouldn't be necessarily months of savings, but it could be. Okay? So on step 4, we need to collect and verify the process data that we're putting in. Well, the nice thing about Art of the Possible is because we all, through 3 bases, talk the same language, and we have to know in great detail our data for each gate. So that's already done for us. Every unit, every squadron knows their data very well. So normally that might take a week to gather that data. So in this case, we already have it. Okay, then we have to input the data into the model. And I talked a little bit about how you do that, the radio buttons and the edit boxes. And that for us would take maybe 2 hours, and I'm going to get a little more into this too in the next slide. So now about 10% of the remaining time to develop a model would just be the fine-tuning. And as you get in here and load data and start to talk about things, you realize, oh, I've got an equipment constraint right here. Let me add some blocks to that model to make it more realistic. Okay? So what is our methods? Or that might take another week to fine-tune it. That's always going to happen in any kind of template you have. So have we used it? We've used it on the C5 gated process, and that actually, we did that model and we actually took it to basically a conference of a bunch of generals so they could see what we were doing. And it also helped the squadron understand the true impact of all the different resource constraints that they were having. We did a model on the C5, or sorry, the C130 gated process. And then we also did one on a shop, the fuel bladders out of the C130. There's basically rubber fuel tanks inside the wings that get taken out. They get checked for leaks. It's one of those that seems like a really simple process, but the way they had set up, it assumed it was like a step-by-step process, but it wasn't. A guy got a bladder, and he stayed with that bladder through all the processes. So what happened there was the customers, which would be the aircraft trying to fly again, would complain about stuff arriving late. We weren't getting it. So we were able to model this and realize that, okay, if you're working on bladders and you already have 10 bladders on your shelf that you haven't started working yet, and more bladders show up, you call the customer and say, these bladders that just showed up, we can't deliver them in the time agreed upon. So similar situation that we had yesterday. Oops, wrong way. Make the planes fly again. Okay, so this is my last slide. And this is the process that we go through with using the template. So a modeler and a process engineer will get together. We're both familiar with the gated process, so we're talking the same language, so I don't have to take hours to explain the template. It actually takes about 30 minutes to explain it. And then both people step through this template gate by gate. Okay, what are your numbers for this? What are your values? What things might be different? You don't model in the things that you find out that you have to add. You don't do that then, or otherwise it takes too long. You just get the data put in there. Because at that point, you're 90% done. And then the last part is you take what you discovered that you needed to add, find out the dependencies and resource constraints, and add those in. So that is what I have. Are there any questions?
This was really cool to see. I saw a similar templating approach happen in the healthcare space, and a lot of that stuff is really tangled and complicated. So you seem to have encountered the same issue where, you know, a lot of people will fit that template really well, but then there's the occasional department, you know, or unit that, gated process that has a lot of extra resources, extra steps, all that other extra constraints that need to be managed within that section of the template. So how do you scale that when you've got, you know, 10, 20, 50 gated processes that depend on each other, and one of them is particularly complicated and deviates from the template? I guess I'm looking for scaling, answers about scaling this process. That's what I'm trying to say.
Okay, so how do you scale this either up or down? The nice thing about doing this is it'll start to show you where you need to focus at the shop level, or the mechanic swinging the wrench around. I guess they turn wrenches and swing hammers. And then the scaling up would be 2 departments would have their template done. Because of that, you learn so much about the system and what's important and what's not, that you may end up having to create a specific model for that. We haven't come up with a method to link them together, because the way we operate, it doesn't matter that much. Any others? No? Okay. Well, thank you, everybody.